In RH criteria, that is in the stability analysis module, in RH criteria we were knowing how many number of roots are present in the right half of the S-plane, and by counting the number of roots present in the RHS side of the S-plane, we were telling that the system is stable or unstable depending on the uh, roots, depending on the location of the roots. But we were not knowing which roots are exactly on the right half of the S plane and how many roots are present on the left half of the S plane. And in the next method is root locus. In the root locus, we knew that the total number of roots we obtained from the transfer function are present on the present on which location and how they are moving, in which direction they are moving, whether they are finite or infinite, whether the system is stable or not. Not to make it as stable, what we need to do, that we discussed there. That is the advantages than RH criterion, because in the RH criterion we were not knowing the total number of exact roots which are present on right half of the S plane, now to make the system unstable. But in the root locus we knew the roots which are present in any of the S plane, so in any of the axis in the S plane. And in the same way, in Bode plot, why we are studying this Bode plot, because here we can find out the marginal gain value, that is the magnitude value or angle value. So in it is the marginal values in order to make the system unstable. So we are not leaving the system to go for instability. So we need to keep the system in stable condition. So we know that which is the marginal value that we can apply for the system in order to keep the system in stable state. So it will be in a border. So if we increase or decrease the magnitude value or phase angle value, it may move to unstable state. So we can control it by using this frequency domain response, that is frequency plot. So before plotting this graph, we need to know some basics. We already know that the semilog sheet we are using, and here there are two axes, that is with different scales. X-axis is non-linear and y-axis is linear, and there are some certain measurements we need to take before plotting the graph. Which are those? And here observe this magnitude scale. I am considering 0 to 20 dB with 10 divisions. Here 10 divisions are there in between 0 dB to 20 dB, and 20 dB to 40 dB also there are 10 divisions. So for each 10 divisions I am considering it as 20 dB. So this is the reference I am taking in this condition. So in order to make the standard measurements, that is in order to find the standard inclinations, I need to find out the angles for each slopes. So I should always consider one decade, the complete decade. So the complete decade is starting from here to here. Total 10 divisions we need to consider, 0.1 to 1. This is one decade. Always while considering the standard inclination values, you should go for one decade, complete decade. Not from here. You should not consider only one division. You should consider the complete one decade. So here I am considering one decade. So this is the point I am considering, starting from here till 20 dB. This is the one division I am taking. So for here it is moving from 20 dB to 0. So it is decaying, the magnitude value is decaying. So I'll be calling this slope as minus 20 dB per decade. This is the standard slope. If we are considering the 10 divisions as 20 dB, this is the standard slope. So in any problem, if they ask to plot the 20 dB per decade, you need to always consider this angle or this inclination itself for minus 20 dB per decade slope. And for 40 dB, here also you should include one decade completely starting from 0, and here 40 dB to 0 it is decaying, that is there is a decrease in the magnitude value, that is gain value, it is decreasing from 40 dB to 0 dB. What is the difference here? It is decreasing, so consider negative sign minus 40 dB per decade. So it is decaying or decreasing the value from 40 to 0 dB in one decade. So per decade we are considering. And also for 60 dB, the gain is decreasing from 60 dB to 0. This slope is called as minus 60 dB per decade, and we can consider the inclination now. And also from the negative values also we can find out the slopes. So it is increasing value, so minus 20 dB to 0, this is a increasing in gain or magnitude. This is plus 20 dB per decade, and this is plus 40 dB per decade. And we can find out the angles. These angles are very important while plotting the Bode plot. So for minus 20 dB per decade, this is for 10 division scale here, and always observe for 10 divisions I am considering 20 dB, so the inclination will be different. If I consider 20 dB for 5 divisions, the inclination will be different. So you need to stick on to a single scale, whether 5 divisions or 10 divisions. Better consider it for 10 divisions itself. For 10 divisions it is 20 dB, means for minus 20 dB per decade, what is the inclination angle? 26 degree. And for minus 20 dB per decade, what is the inclination? 45 degree. And what is the inclination for minus 60 dB per decade? It is 56 degree. So these are the standard degrees if you consider 10 division equal to 20 dB scale. And also in other case, you can also consider 5 divisions equal to 20 dB also. Then the angles will be different. So the angle for minus 20 dB per decade will be 14 degree, and the angle for, so you always consider 0 as a reference line. So to 0th line, 0th reference line. So for 40 dB, for minus 40 dB per decade slope, the angle will be 26 degree, and for 60 dB per decade, it is 37 degree. So these are the standard inclinations. We need to make use of these angles while plotting the Bode plot. You need to remember both the cases, 5 divisions equal to 20 dB as well as 10 divisions equal to 20 dB. So these are the standard inclinations.